Okay, good morning everyone, and welcome to one of a series of webinars on digital radiography. So today we will be talking about DR panels or DDAs and the major differences between them and how you would choose the correct one for your particular application. This is the same webinar I did a few months ago. So if you did attend this, it's probably, the content will be very similar. There is a Q&A section in Teams. You can post questions at any time there and I will answer them at the end. So first of all, I'm Nick Adamo. I'm the head of software for NDT, based in Malaysia. And also the obligatory company intro. So we are NDT, a German company, based in southern Germany. We do digital radiography for NDT. We're present all around the world, represented by dealers all around the world. And where I am is our software development headquarters. What do? We do both hardware and software. So in terms of hardware, the two major categories are computed radiography and direct radiography. Of course, we develop and sell the software to go with these two products. And we also do traditional film radiography, the chemistry, and we have a automatic film processor as well. But today we're talking about flat panel detectors. So they have a few different names. I think I've called them DR panels already. So a lot of people use different names: DR panels, flat panel detectors, DDAs. But let me explain what it all means now. So DR might be a confusing term to use actually, and I usually call them DDAs, but let me just explain what DR is first. In this context, in the context of DDA, DR is direct radiography. Why direct? The direct means we more or less measure the radiation directly. There's no processing step in between. There's no film to be developed. There's no imaging plate to be scanned. We're directly measuring the radiation. So that's why it's called direct radiography. The device is a DDA. Because it's a digital device, of course, it needs power, and it comes in a range of different sizes with many different various performance attributes, and that's what I'm going to talk about this morning. So hopefully by the end of it, you'll have a good idea of if you see a data sheet or a product brochure for a DDA, you'll be able to understand what everything means. Okay, why DR, direct radiography? Why DDA? The images produced are extremely high quality. When I say high quality, I'm more or less referring to the signal to noise ratio, which more or less correlates to the contrast. So we get really high contrast images with a DDA. The other nice thing is we get the images in real time. I mentioned before there's no processing step. So you don't have to wait 8 or 9 minutes to develop the film or a few minutes to scan the imaging plate as with CR. And a third nice reason is DDA panels are very low maintenance. There's no moving parts, there's no consumables, there's no chemicals, right? There's no imaging plates or anything that wears gradually, generally speaking. How do they work? So a DDA actually converts the high energy X-ray photons into visible light and we simply measure the intensity of the visible light. And the material that does that conversion is called a scintillator. So there's a nice little image here. The X-ray comes in. In the scintillator, it's converted to visible light, and below the scintillator, we have more or less a camera sensor, which we get a digital signal from, and thus a digital image. Okay, so different attributes of a DDA. The blue parts I'll be covering in this presentation. So there's quite a few, so let's get into it. First one is an easy one, the active area. You've probably seen panels of various different sizes, and there are reasons that they are certain sizes. So I want to just point out this one down here. This is one of our high energy panels, the DRC2430HE. So you have this active area here, and then this surrounded by the non-active area. So when I say active area, I mean the area that can actually read the X-ray radiation. So the reason we have this non-active area is the electronics is moved away from the active area, and this allows you to shield the electronics separately without blocking where the radiation needs to go. So usually the panels which are designed for high energy applications with cobalt or iridium or things like that, they'll have this design. Conversely, panels which may be for lower energy, selenium, X-ray, still okay with iridium as well, will have this smaller design with very little. There's a bezel usually, of course, but very little non-active area. Okay. And I think I've more or less covered this one. So why do we separate or move away the electronics? It's because the electronics is quite sensitive, especially memory chips are quite sensitive to high energy radiation. They can be damaged. So a DDA usually will have internal shielding, and as I just mentioned, if the electronics is moved away from the active area, you can shield that separately. You can have lead shielding, and we also, with our high energy panels, we offer that shielding separately if needed. Of course, there's drawbacks to shielding, to adding additional shielding. It makes the panel heavier because shielding is not lightweight. But nearly every DDA has internal shielding already, so you can use them without this additional shielding, usually definitely with X-ray radiation. Isotopes, you may need this external shielding. But the spec, the datasheet or the brochure usually should tell you the recommended maximum energy for the particular panel. In this case, this datasheet says 350 kV. So that's one thing to check when choosing the panel. Next one is the pixel pitch or pixel size. Usually it's the same thing because the gap between the pixels is usually 0. So smaller pixels, higher imaging resolution. We offer panels from 76 to 200 microns. So you need to choose appropriately here as well. If you don't need, you know, high spatial resolution, you probably don't have to choose a 76 micron panel. 76 micron panel will have bigger file sizes, so longer transfer times from panel to PC, and bigger pixels generally usually also means you collect more photons. So maybe better quality images with bigger pixels. So you need to choose the pixel size depending on your target application. I just mentioned the word spatial resolution, and I think it's important just to define what that is. It's basically the size of the smallest detail that can be differentiated from another thing in the image. And we must use a duplex wire IQI to measure this. And the third point on this slide says, yes, it largely depends on the pixel pitch, but not just the pixel pitch. So just because you have a 76 micron panel, it doesn't mean the SRB is 76. It could be a little bit higher, maybe 80. And you must use an IQI, a duplex wire IQI to measure that. And luckily, our software in particular, does make this easy. You can automatically measure the SRB by just drawing a line across the IQI. Another thing you might see in data sheets for a DDA is the bit depth. So it's essentially the number of different gray levels. Most of our panels, except one, I think, is 16-bit, and that's over 65,000 different gray levels. Higher bit depth, usually higher dynamic range, larger, generally larger image file size. It depends here, but usually the higher bit depth would be, I would say, I would choose that over a lower bit depth panel. And we have a nice diagram here kind of explaining, a bit exaggerated, but explaining the difference between different bit depth for grayscale images. Okay, scintillator. I already mentioned that the scintillator is the part which converts the radiation to light, to visible light, I should say. There are different scintillators. In this slide, I've listed the different Gadox scintillators, and there's a trade-off. The high resolution, so on this axis, MTF, the high resolution scintillators are less sensitive, so they emit less light. That's what I mean. That's why it says brightness here. So you can't have really high resolution and high sensitivity, unfortunately, at the same time. So you need to actually choose your scintillator based on your application. So maybe if you were using isotopes, you would use the plus. If it was X-ray, maybe fine or ultra high resolution. So just be aware, there are different types of scintillators, and it's they do perform differently. Under the scintillator is the sensor, like a camera sensor. There are also different types. The most common in NDT is TFT, amorphous silicon. This can be manufactured in large sizes, so especially the large panels in NDT are amorphous silicon, and the smaller panels with smaller pixels in NDT are usually CMOS. We have a DR7, a really small 25 micron pixel pitch CMOS detector. So CMOS gives you it's the smaller pixels compared to amorphous silicon. And again, it's a trade-off, as you can see in this diagram. So large TFT, you can get large active areas, easy to manufacture large panels for TFT, but the pixel sizes are generally larger. So again, application dependent. An easy one, panels usually have different connectivity options. These days, most Ethernet, at least Ethernet for connectivity, gigabit Ethernet, and certain panels which are designed for in-field use will have Wi-Fi as well. And just a few things to keep in mind here. Ethernet, the protocol itself does have a maximum cable length. It's around 100 meters. Of course, you can extend that with additional equipment, but just letting you know there are limitations here. Wi-Fi as well. Panels will perhaps offer dual band, 2.4 and 5 at the same time. And you also need to choose this appropriately as well. For example, 5 gigahertz usually has a lower range compared to 2.4. And if you do have a lot of obstacles, for example, if you're using this panel in a concrete bunker, Wi-Fi could be challenging. Perhaps Ethernet may be a better option there. A lot of panels, nearly most panels, especially standalone panels, will have battery power. Some may have 2 batteries where you can hot swap the battery. If one goes flat, you can do the hot swap without turning the panel off. Many panels also allow you to power them permanently with an external power supply. And there may be an additional kind of external box needed to do this. But usually when you're powering it externally, the panel's in a fixed location, maybe in a cabinet or in a bunker, and having this extra box isn't really an issue. Ruggedness. So the big over here, these 2 kind of lists. This is the IP level. Ingress protection is sometimes a name for that. So something else to check, especially if you're using the panel in field. So as an example, our DRC 24330 is IP67 rated, dust proof and waterproof. Not every panel has an IP rating, and in that case you may have to use maybe a special mounting frame to protect the panel a bit more. And these mounting frames are quite handy sometimes because they do allow you to easily mount, as the name suggests, to easily mount them to pipes or other objects, because they do have these attachment points on the sides. Also drop tests. A lot of DDA spec sheets will give you drop test information. Again, our DRC 2430 is 1 meter drop tested. So important thing to keep in mind if you're using the panel in field, because they're not cheap devices, so dropping them can cause damage. This one is really more important for real-time radiography. How many frames, the frame rate, how many frames the panel can acquire in 1 second is the frame rate. So you may know with panels, you can average the frames together and get a higher contrast image, higher SNR, which is nice, especially when you're working with isotopes. And the frame rate can help you here. So just something to keep in mind, but generally for field radiography, we don't particularly worry too much about this. Okay, an important one, a very important one, I would say, is the software, because DDA, it does require calibration, and it does make it a lot more user-friendly if the calibration process is easy. So a very important consideration when choosing a panel is, I would say the calibration process. You really want to look for software which makes this easy for you, because You will be performing various calibrations as you use the panel. It's not something you just do once. You periodically do them. So if you have a software that makes that easy, it really helps. And of course, all the tools to go along with digital radiography, the software should have them. SRB measurement, SNR measurement, image filters, enhancement, those kind of things. So here in this slide are some screenshots of our detector software. Okay, I've reached the end. So in summary, you really need to first work out your application, of course, that's the first step. What are you looking at? What is the smallest defect you need to see? And then also what X-ray sources are available to you. You know, if you're working in the field, you may only have isotopes. And the type of item you're inspecting may determine the radiation source you need. If it's a really thick material, you may have to use iridium or cobalt. So all these things you need to know before you can really choose a DDA, because it does drive a lot of the decisions, especially with shielding and pixel size and the size of the panel itself. There are other important things to consider: warranty, cost, software, like I just mentioned. Best thing to do is to discuss with your vendor your requirements, and us as a vendor, we're always happy to discuss any applications you may have for DDA, DRT, direct radiography with DDA panels. So if you do have a particular application which you think may benefit from using a DDA panel, I'm always happy to discuss and advise on that. Before we finish up, just wanted to show you what we do offer. This is a nice summary of our product portfolio. So on the y-axis is the size of the pixel, and on the x is how big the panel it is. So on the right side now kind of covers what the typical applications of each panel may be. So of course, small pixel sizes gives you high basic spatial resolution, which is usually ideal or required for aerospace. And then going up a level, welding requires moderate spatial resolution. So our DRC and DRA range would cover that. And profile radiography, castings, usually doesn't require super high resolution, so you can use panels with higher pixel sizes. So our DRA or DRP range perhaps could be appropriate for those applications. But if you do have specific applications, please do ask me, and I can probably give you a better suggestion on which panel might be suitable. This is a bit more of a summary of the individual applications and what we need to think about per application. For example, let's have a look. So if you're using the panel in a cabinet, you don't really care too much about portability or ruggedness or Wi-Fi. And usually castings as well is done not in field. So again, portability and Wi-Fi doesn't really matter. And like I mentioned before, profile radiography usually doesn't require super high resolution. So this slide gives you just, you know, shows you what you should be thinking about for each application, or what is important. Hey, that is the end. And as I mentioned, please do contact me if you have specific questions on a certain application.